Here I show the equation for bulk modulus, and you can see it's similar in form to Hooke's law. Hooke's law in 1D is this: Young modulus multiplied by a strain. But if you're looking at volumetric strain, and so you'll be looking at a mean stress. And what's the mean stress? Sum of the three principal stresses, S1, S2, S3, divided by 3. This elastic modulus will be bulk modulus when this is volumetric strain and this is mean stress. So you can make this the subject of the equation, and what you're left with is mean stress divided by volumetric strain. And that's precisely what this is, right? Because this is the mean stress and this is the volumetric strain. There is a similar expression for shear modulus, but only uses stress on x face in the z direction divided by strain on the same face in the same direction. And remember, this is same as this, right? Mu, which is the second Lamis constant, is same as shear modulus. At the end of the last meeting, I gave the expression for volumetric strain, which is just the sum of the diagonal terms in your strain tensor, right? And the diagonal is epsilon xx, which is same as epsilon x, epsilon yy, epsilon y, and epsilon zz. So the trace is the sum of the diagonal terms, and that is your volumetric strain. Notice here is just the trace, whereas for for mean stress is a third of the trace. So that's mean. Mean means average, right? Whereas volumetric strain is just a trace of the strain tensor. And it could be written in these different forms. Now we can actually derive the volumetric strain for 2D using this illustration right here. So this is the original dimension of the object, is x by y. Then after deformation, x direction expands by delta x, y direction expands, or it expands in the y direction by delta y. It's exaggerated, so you can see it. Normally these changes are very small, right? That's the assumption in the Cauchy stress tensor. So we can express, this is the exact definition of volumetric. Let's start from here. Volumetric strain, delta V, change in volume per unit volume. Which volume is this? Is it before deformation or after? It's before deformation. So what's the volume before deformation? X times y, length times breadth. So how do you get the change in volume? What's the volume after deformation? Y plus delta y times x plus delta x. So x plus delta x times y plus delta y. Volume after deformation. Volume before deformation, x times y. So that's your change in volume per unit volume. We can expand these products right here. X times y plus x times delta y plus y times delta x plus delta x times delta y, and you still subtract the initial volume and divide by initial volume. And you can now, this term goes away right away, right? They're the same. And you're left with only 3 terms. What's x delta y divided by xy? X cancels out, right? So you're left with delta y over y. And what's delta y over y? Sigma yy. How about this? Y cancels out, right? So you're left with delta x over x. What's delta x over x? Sigma xx. Strain in the x direction. And this is delta x times delta y divided by x times y. So that's epsilon xx, which is this, and times epsilon yy, which is this. And that's your expression right here. And because this is a small value, right, based on the Cauchy stress tensor assumption, small deformations. So small value multiplied by small value, a much smaller value that tends to 0, you can neglect that term and write out your volumetric strain in this form. So for 3D, all you need to do is to add the third component, right? Epsilon ZZ, which is precisely this, and that is the trace of the strain tensor. And this assumes you're applying normal stresses, right? It's the normal stresses that change the volume. And so we have deviatoric strains, deviatoric stresses, and we have volumetric strains, volumetric stress. And so normal stresses produce volumetric strains. Deviatoric or shear stresses produce deviatoric deformation or deviatoric strains. And so in the more generic sense, here it was all normal stresses, right? In the more generic sense, you could have shear, and that will result in angular deformations, and you will have to use the full strain tensor and the full stress tensor as are given in the Hooke's law section for anisotropic solids. You can also do the same calculation in 3D, and you will have change delta x, delta y, delta z, and you will arrive at this expression. For porous rocks, which are saturated by fluids, we don't use stresses. We don't use total stresses. We use what? The effective stresses, right? The part of the stress that acts on the grains, on the pore structure. Elastic moduli and seismic wave velocities. I had mentioned that you're able to estimate the elastic moduli from the seismic wave velocities, P wave and shear wave velocities, because the elastic properties, or better still, the seismic wave velocities are a function of the properties of the material through which it passes through. And this is how we can estimate those elastic properties. So you have two equations in two unknowns. The two unknowns are K and G, bulk modulus and shear modulus. Bulk density, we assume it's known. We can get that from well logs, and that's pretty much an input. So two equations, two unknowns, the equation is completely defined. And then you can calculate K and G as a function of Vp and Vs. For liquids, shear modulus, shear S-wave velocity is 0. Why? Liquids don't support shear stresses. This numerator right here is the P wave modulus or M modulus, and you can square both sides. This becomes Vp squared, and then multiply both sides by rho, so you get rho v squared as this. So that is the expression to calculate M modulus directly from your P wave velocity. This is the expression to calculate Poisson ratio as a function of P wave and S wave velocities. And for liquids, Poisson ratio is practically 0.5. I mentioned this on the previous slide. And the common value for solids is, the common value for Poisson ratio for solids is 0.25. And I explained in class that you can basically set this to 0.45, which is 1/4, and go through the algebraic calculations I showed, which is basically multiplying, cross multiplying, right? So this becomes equal to 4 times this. Then eventually divide both sides by Vs, and you get this expression right here. Make sure you can do that. I like to ask those kinds of questions in exams. Notes on poroelasticity. Yeah, it was total stress for normal materials, but for porous materials filled with fluids, then we use the effective stress and not the total stress, because we partition the total stress into the effective stress and the pore pressure. And this is your Hooke's law for a pore-filled rock. Rock strength, frictional strength are dependent on simple effective stress, which is same as the Terzaghi effective stress. Rock strength for solid material is, you need to exceed the rock strength before you create a fracture. But if you already have a fracture or fault in the system, well, the frictional strength of that surface controls when you begin to have frictional sliding of the rock across that fault surface. I explained that in poroelastic materials, the elastic moduli are flow rate dependent because of that concept of dispersion, right? Undrained rock appears stiffer than drained rock. I had explained that using this tennis ball filled with water with a small hole. So the rate at which the fluid can escape from the tennis ball is the analog to your flow rate in your reservoir. If the fluid can't flow out of the formation quickly, and you apply a stress suddenly, then the stress builds up and the material appears stiffer than it really is. And I will explain this in a separate video.